Okay, let us continue with our atomic theory. In the last class, we learned about a new atom model, the Rutherford atom model, also called the planetary atom model. And that planetary atom model was the result of Rutherford's famous gold foil experiment, in which he bombarded a gold foil with alpha particles. So from the result, he concluded that the atom must be essentially empty space, and there is a heavy positively charged nucleus, and the electrons would move in orbits like planets would move around the sun. So overall, the atom would be approximately 10,000 times larger in terms of radius in comparison to the nucleus. So we also discussed that there are major problems with this model because an electron is a self-accelerating charged particle when it moves in an orbit, and as such, it should emit electromagnetic radiation constantly. But under normal circumstances, atoms don't emit such electromagnetic radiation, and even if the electrons did that, then that would mean that the atom wouldn't be stable. The atom would need to collapse because the electrons would constantly lose energy and spiral down into the nucleus. So we then also already discussed the beginnings of Bohr's atom model. So Bohr knew about the problems associated with the Rutherford atom model, and he developed an improved atom model, which is now called the Bohr atom model. And we began to discuss what led to Bohr's atom model. We also said that there were actually two major contributions or two major influences that led to the Bohr atom model. The first one was the discovery that energy was quantized, and the second one was that atoms could absorb and emit electromagnetic radiation under certain circumstances, but the wavelengths would be quantized. We already talked about the first part, the quantization of the energy, which was discovered by Max Planck, who developed or assumed that energy was quantized in the form E is equal to n times h times nu, in order to explain, well, the wavelength and the intensity distribution of that blackbody radiation, which is correctly described by the Planck equation that you see here. We talked already about blackbody radiation, but I wanted to build on this further by showing you a little applet to which you have a link here, and I'm just switching the screen so that you can see this in more detail. And this again becomes more complicated. Because I cannot see this here, so wait a moment, please. Why is this not working? So I don't know why I can't get out of my presentation here. I cannot end this presentation. It's not letting me do that. Oh, wait a moment. Now everything becomes completely messed up, it seems. So in show, we have to go here. And then we have to go here. And then we have to click new share. All right, now you should all see here a little applet, which is associated with Blackbody radiation. So you see here the wavelengths of the radiation versus the, well, intensity of the radiation for different temperature, which you actually see on this side here. So here we are at pretty low temperature, and you see that the wavelengths are well above the visible region. Okay, but now we can increase the temperature, for instance, to the intensity of a light bulb. Yeah, and you see that, well, now the intensity goes way up, and we have also contributions in the visible region. And if we actually just adjust the y-axis here, we see that now the maximum is still in the IR, but we see that we have a lot of intensity here in the visible already. And now as we increase the temperature further, intensity further goes up, but also the wavelengths become even shorter. And when we are here at the temperature of the sun, which is approximately 6,000 Kelvin, then we see that we have the maximum in the visible. Okay, so the maximum is actually in the green region, but of course the sun also radiates light of longer wavelengths in the yellow and in the red region, but also then in the blue, in the violet, and even in the UV region. And if we increase the temperature even further, well, the intensity would further go up, right? So here is Sirius A, which is a different star, and that star has an even higher temperature. And then we would have our maximum even in the UV region. Okay, so this just as a little appendix to what we discussed in the last class. So now let's move on from the Blackbody radiation, which led to the discovery that energy is being quantized, to the discovery that the atomic absorption and emission spectra are quantized. So it was discovered that under certain circumstances, for instance, when you place or put an element into a flame, then that element could emit light in a particular region, but it could also absorb the same light of the same wavelength. And these wavelengths would be very discrete. They would be quantized, and these wavelengths would be associated and characteristic with a particular atom. So you see here the absorption/emission spectrum of the hydrogen atom, and you see that the hydrogen atom can absorb and emit electromagnetic radiation of 4 discrete wavelengths. So 2 of them are in the blue. Here, this one is at somewhat higher wavelengths. It is light blue, and here we have another one, which is in the red region of the visible light. So these 4 lines are called the Balmer series of the hydrogen absorption and emission spectrum. So hydrogen, like other elements, cannot only absorb and emit in the visible, they can also do this in the IR and also in the UV. Okay, so for the hydrogen atom, the respective series of lines is called the Paschen series, and the respective series of lines in the UV is called the Lyman series. So now, of course, scientists have thought, well, is there a pattern that these lines follow? And can you actually cast that into a formula? And the answer is, for the hydrogen absorption emission spectrum, you can fairly easily do this, both for the wavelength as well as also for the associated energies, right? So for a wavelength, there's an associated frequency, and that is linked through, well, the formula nu is equal to c over lambda. And then the energy, there's an energy associated with the frequency, and that's given by the formula E is h times nu. Okay? So now the energies associated with these lines is empirically found to be a constant times 1 over an integer number square minus 1 over another integer number square, whereby the second integer number is higher than the first integer number. Okay? So you see that in order to explain or not explain them, but in order to, well, describe the spectra of the atoms, one again needs quantum numbers. We can also call them integer numbers. So now Bohr draw the following conclusion from that. He argued that the quantization of the atomic spectra must have something to do with the quantization of of energies, of energy. And that because energy generally comes in discrete quanta, the energies of the electrons could also only come in discrete quanta. Okay, so now if the energies of the electrons are being quantized, then that means that the radii of the electrons in the orbits must also be quantized. So in contrast to what Rutherford assumed, the orbits, or the radii of the orbits, couldn't be arbitrary. Only very specific orbits would be allowed, meaning that these orbits would be quantized. So the most inner orbit would be associated with the, well, lowest energy of the electron. Okay, and the second highest orbit, sorry, this is the lowest one. The second highest orbit, second lowest orbit, would be associated with a higher quantum number, n equal to 2. So the third orbit would be then associated with another quantum number of n equal to 3, and so forth. And using that concept, one could explain the atomic spectra in the following way. One could say that in order to make an electron jump from a lower orbit to a higher orbit, that electron must absorb electromagnetic radiation. And because the energy difference between the two orbits would be discrete, okay, the wavelength and the energy of the absorbed electromagnetic radiation would also need to be discrete. Okay, vice versa, an electron could only emit electromagnetic radiation of a specific wavelength, because that emission would be associated with a jump of the electron from an outer orbit to an inner orbit. So because the energy difference between that outer orbit and that inner orbit is discrete, also the energy of the electromagnetic radiation associated with this jump would be discrete, and that means it would be quantized. Okay. Now, this picture is a qualitative picture. Now let us see if one can also calculate the radii of the electrons in the orbits, as well as the actual electron energies. Okay. So now in order to do this, Bohr made two assumptions. So the first one is that the centrifugal force is equal to the Coulomb force. Okay, so the centrifugal force associated with the movement of the electron in the orbit would tend to move the electron away from the nucleus. Okay, and that force would be counterbalanced by the Coulomb force, the electrostatic attraction between the electron in the orbit and the nucleus. And only if these two forces were equal, then the electron would be stable in the orbit. So this assumption is actually nothing new. This assumption was already made by Rutherford. But now the second assumption is really new, which argues that the angular momentum of the electron in the orbit is quantized. Okay, and that's a consequence of the assumption that the energy of the electrons in the orbit must be quantized because of the quantization of energy. So the angular momentum could only be, which you see on the left side of the equation, could only be an integer number times the Planck constant h. Okay, so now you see here a number of variables. Okay, so on the left-hand side, you see here the formula for the centrifugal force, okay, which contains the mass of the electron, the velocity of the electron square, and the radius, the distance of the electron from the orbit, electron from the nucleus. So this is the formula for the centrifugal force according to classical mechanics. So here on the right-hand side, you see the formula for the Coulomb force between two electrically charged elementary particles, namely the proton, which is in the center of the atom, and the electron, which is orbiting around the proton. So the proton has one elementary charge and the electron has one elementary charge, and the Coulomb force that attracts the two to each other is given by this formula here, that this is the elementary charge square over 4 times pi times the dielectric constant of the vacuum times the distance of the electron from the nucleus square. Okay, so now what about here? Here again, the velocity of the electron appears, the mass of the electron, as well as the distance of the electron from the nucleus. We here see the introduction of the quantum number n, as well as the Planck constant by which the quantum number is multiplied. Okay, so that means nothing else but that the angular momentum of the orbital would need to be an integer multiple of the Planck constant. So now we can make mathematical rearrangement. We can solve this equation here for the velocity of the electron, And then we will get that the velocity of the electron is equal to n times h over 2 times pi times r times m. Okay? So then we can take this term here for v, and we insert it for this v here in equation number 1. Okay? And then the overall equation becomes this, which says that we have m times n squared times h squared over 4 times pi squared times r to the power of 3 times m squared is equal to e squared over 4 pi epsilon 0 r squared. Okay, so now we are looking for the radii, allowed radii for the electron in the orbits. So what we can do then in the next step is trying to solve this equation here for the radius. Okay, so we will do now additional mathematical transformation that solves this equation for the radius. So this only requires simple algebra. So here you see again the equation from the previous slide. So what we can do with it is we can multiply it times 4 pi epsilon 0 r squared. Okay, so now what do we get? Well, then on the right hand side we have only e squared. On the left hand side we'll have overall n squared times h squared times epsilon 0 over pi r m. Okay, so now we need to solve this for r, as we discussed previously. So we can divide this equation by e squared and multiply it by r. Okay, so then basically we bring r to the right side, okay, and eliminate e squared here on the right side. And that gives you the final result, which is that r is equal to n squared times h squared times epsilon 0 over pi times the mass of the electron times the elementary charge square. So now what does this result mean? It actually means that the radius of the electron in the orbit is only of a function of a quantum number n, demonstrating that the radii are being quantized. All the other parameters that we see here are just constant. So h is the Planck constant, epsilon 0 is the dielectric constant of the vacuum, which is a constant, pi is a constant, the mass of the electron is also a constant, and the elementary charge is also a constant. So basically the radius is a constant times n squared. And now, of course, we can calculate the explicit radii by entering the quantum numbers n and just calculate using the values for the other constants here. So for instance, if you enter n equal to 1, then the radius becomes, well, 1 squared times h squared times epsilon 0 over pi me squared, which is equal to 5.29 times 10 to the power of minus 11 meters. Okay, so this is now a phenomenal result, in my opinion, with very simple mathematical assumptions and transformation. We can calculate the first radius of the electron of the hydrogen atom, and we can calculate all the other radii as well. Okay, we just need to insert different quantum numbers into the formula, 2, 3, 4, 5, and so forth. So now we have done the first step, we know the radii. Now let's go to the second step and calculate the energy of the electrons on these radii. All right, so now how do we approach this? Well, generally, the energy of the electron will be the sum of the kinetic energy of the electron plus the potential energy of the electron. So now must find appropriate terms for the kinetic and the potential energy respectively. So let us look first at the kinetic energy. So according to classical physics, the kinetic energy of a particle is given by this formula here. It's a half m times the velocity square. Okay, so now we remember that in our first equation that we used, the centrifugal force was equal to the Coulomb force here. So what we can do is we can solve this equation for v square, okay? And then v square is equal to e square times 4 pi epsilon 0 r m. Okay? So now in the next step, we can insert this term for v square into this equation over here. So we substitute this v square here by this term. And then our term for the kinetic energy overall becomes, and I'm omitting here a few intermediate mathematical steps, is e square over 8 pi epsilon 0 r. Okay, so now we see that our kinetic energy is a function of r, and we know that r is being quantized, so our kinetic energy is expected to be quantized. Okay, so now let us look at the potential energy. So the potential energy is the first derivative of the Coulomb force, okay, and it's given therefore by this formula here, which is equal to minus e square over 4 pi epsilon 0 r. Okay, so that is the potential energy due to the Coulomb attraction, okay, between the electron and the proton. So now, in order to get the overall energy, we just need to add up the kinetic and the potential energy of that electron, okay? So this is now done here. So that's e square over 8 pi epsilon 0 r minus, well, now this term here, e square times 4 pi epsilon 0 r. And that is, when we factor out e square over pi epsilon 0 r, it's that times, well, 1/8, okay, minus a quarter, which is minus e square over 8 pi epsilon 0 r. I should probably make a comment here where this minus sign is coming from. So this minus sign here is because the Coulomb forces between the electron and the proton are attractive. And this minus sign here is because this energy here represents a binding energy, which is negative because adding an electron to the proton to produce the H atom is actually an exothermic process, okay? So binding energies are always negative energies because the addition of a free electron to the nucleus is an exothermic process. All right, so now we see that the overall energy is a function of the radius r, which is quantized. So we can now insert the term that we have previously calculated for the radius r. Okay, so that term was n squared times h squared times epsilon 0 over pi m e squared. Okay, so if you take this term and insert it here, then the equation becomes this here. Then you see that now E is equal to minus the elementary charge to the power of 4 times m over 8 epsilon 0 squared times n squared times h squared. And this is now our final result. And we see again that that also the energy is only a function of the quantum number n. All the other terms are constants. So the elementary charge is a constant, the mass of the electron is a constant, well, 8 is a constant, the dielectric constant of the vacuum is a constant, and the Planck constant is also a constant. So overall, the energy is a constant over the quantum number n to the power of 2, the quantum number n squared. Okay. Therefore, the energy levels of the electrons in the hydrogen atom are basically a function of, well, 1 over n squared, constant over n squared. Okay. So now we have calculated the radii and we have calculated the energies of the electron in the orbit for the hydrogen atom. So now, of course, the question is, can we experimentally verify that this calculation is being true? Okay, and for that we can now use the experimentally measured absorption and emission spectra for hydrogen. Okay, now let's do this. So we've just calculated that the energy of the electron in an allowed orbit follows this equation here. So now this gives us now also the possibility to calculate energy differences between different orbits. Okay. So well, that would be then minus e squared, e to the power of 4 times m over 8 epsilon 0 squared times n high square times h square. So a higher quantum number, okay, of an electron in a higher orbit, minus basically the same term, e to the power of 4 times m over 8 epsilon 0 square times now n low square, and that means now a lower quantum number n, times h square. So now that gives, when we factor out this term here, this gives e to the power of 4 times m over 8 epsilon 0 square h square times 1 over n low square minus 1 over n high square. Okay. So now that kind of looks familiar when you consider that we previously found the Rutherford formula that explains the atomic spectra. So remember, here our delta E was the Rutherford constant times 1 over n low square minus 1 over n high square. Okay, so now we can calculate the explicit value for this constant here in front of this term and compare it with the value for the Rutherford constant. And we'll find that they are exactly equal. Okay, so the Rutherford constant is indeed equal to e to the power of 4m over 8 times e squared times h squared. So that means now that the experiment is in nice accordance with the theory. And that's, of course, a very strong argument that the theory is true and that there is truth in the Bohr atom model. And there's truth in the idea that the radii of the electrons are actually quantized. So in contrast to what Rutherford assumed, they cannot rotate in arbitrary orbits around the nucleus. Only discrete orbits are being allowed. And in a sense, that quantization may also serve as an argument why electrons in an atom do not permanently send out electromagnetic radiation and do not make the atom collapse, keeping the atom stable. Okay, so the Bohr atom model was another major step forward in the development of atomic theory because it for the first time introduced the quantization of electron states in the atom. However, it is still not the atom model that we use today because it is still problems. And the first problem is that it can only explain the hydrogen spectrum. Okay, so it fails to explain all the other spectra of all the other elements, and that's of course a major shortcoming. It indicates that something is still not quite right with this atomic theory. And secondly, Bohr's postulates are ad hoc. They lack an explanation, so there's not a really sufficient and satisfying explanation why electrons in an atom should behave so fundamentally different than other particles. Okay, and the answer to this question is that the Bohr atom model does not take into account another property of the electron, which is the wave-particle dualism. And we will see that when we take into account the wave-particle dualism of the electron, that then a refined atomic model, the so-called quantum mechanical atom model, can be developed, which addresses shortcomings and overcomes the shortcomings associated with the Bohr atom model. All right, so therefore, in the following, we must turn our attention to what is called the wave-particle dualism. So the wave-particle dualism was not first discovered for the electron, it was first discovered for the photon and then generalized for all particles, including the electron. So let us now look more closely how the wave-particle dualism was discovered for the photon. And it was discovered in the context of another experimental observation that required an explanation at this time, and this was the photoelectric effect. So the photoelectric effect is schematically illustrated here. So you see here a metal surface containing electrons, and here there is light irradiating that metal surface. So it was observed that when the wavelength of that light was above a certain threshold, then no effect was observed. However, when the wavelength of that light was below that threshold, then all of a sudden, electrons would be emitted from that surface. And this effect is called the photoelectric effect. Okay, so by the radiation of a metal with light, one can eject electrons out of that metal. So Albert Einstein investigated this effect more closely. So he actually measured the maximum kinetic energy these ejected electrons could have, and he plotted that energy versus the frequency of the light that irradiated the metal surface. And he found that there was a very simple linear relationship between the kinetic energy of the electrons and the frequency of the light. So below a certain frequency, well, simply no electrons were ejected. And of course, then the kinetic energy is equal to 0. But above that frequency, electrons were ejected and their kinetic energy increased in a linear fashion with the frequency. So Einstein simply analyzed the slope of this line, and he found that the slope of this line was equal to the Planck constant. And in fact, the kinetic energy of the ejected electrons was, well, the Planck constant times the frequency of the light minus an energy, okay, which we know now is the binding energy of the electrons within the metal. So it takes a certain energy to, well, overcome this binding energy, and then any energy beyond that would be the kinetic energy of the electron. So now the question was how to interpret this, and Einstein thought that this behavior would indicate that, well, light would not only have wave properties, but must also have particle properties. Because then one would assume that, an electron, if the light as a particle, which would now be called the photon, would hit an electron in the metal surface, okay, and only if the kinetic energy of that photon was above a certain threshold, then the binding energy of the electron would be overcome and the electron would be ejected from the surface, whereby the kinetic energy would be nothing else but, well, the energy of the light, which would follow the equation h times nu, minus the binding energy here. All right, so this idea would also explain why energy would be quantized. So Max Planck already assumed this before, but there was actually not a good explanation for this behavior. Why would energy be quantized? And the answer is light does not only have wave properties, it has particle properties. It comes as discrete particles, as photons, and that's the reason why energy is quantized, okay? Particles can only come in integer numbers, and therefore photons can only come in integer numbers, and therefore the energy associated with these photons is being quantized. Okay, one can see the wave-particle dualism of the photon also in the following very simple mathematical transformation. So Einstein already had developed his famous equation E is equal to mc square, which indicated that actually mass can be converted into energy and vice versa. Okay. So now we can replace here E for the electromagnetic radiation just by h times nu, and then mc square is equal times h times nu. Now we can just solve this equation for nu, and the nu is equal to m times c square over h. So if we consider that the relationship between nu and lambda, then we can substitute nu by lambda, and then lambda is equal to h over m times c. And now you see that a wave property, which is the wavelength, is linked to a particle property, which is the mass. And you can see that, well, the longer the wavelength, okay, the smaller the mass must be, and the shorter the wavelength, the higher the mass of the photon must be. Okay? So now originally it was thought that the wave-particle dualism would hold only for the photon. But then another scientist, Louis de Broglie, and I can briefly bring this up as well, had the radical idea that this wave-particle dualism wouldn't hold only for photons, but all particles, including the electrons. And that the wavelength associated with the particle would be equal to h over m times the velocity of that particle. So we simply replaced the velocity of light, which is associated with a photon, by a general velocity that any particle would have. So this was a very radical idea at this time, and Louis de Broglie was only a PhD student when he actually came up with that idea. So originally his PhD thesis was almost not approved because of the radical and unproven nature of this idea, but his idea was confirmed mainly by electron diffraction experiments for electrons and also other particles, so that he finally won a Nobel Prize for the discovery of the wave-particle dualism for electrons and also other massive particles. So currently we believe that all particles, no matter how massive, okay, whether it's an electron or an atom or a soccer ball, will have that wave-particle dualism, even though there are limitations to experimentally prove this, simply because when you use this formula, when this mass here becomes very high, this wavelength here becomes very small, and then it's experimentally very difficult to measure that wavelength. But up to date, no experiment has been performed that would actually disprove the generality of the wave-particle dualism. Okay, I think we can actually stop at this point. So I just stop the recording here.